Good morning, everyone. My name is Pranay. I'm from AIML Section C from IARE College. Today, my subject data structures. As a part of my subject data structures, today I have chosen the topic high quality fault resiliency in factories. And I'm going to explain about the topic. Modern data centers, from the backbone of cloud computing, artificial intelligence systems, and large-scale internet services, these systems are required to operate continuously with near zero downtime, making fault resiliency a critical design requirement. Traditional network topologies such as a simple tree and bus structures suffer from the problem of single point of failure where a minor fault can disrupt a large portion of the network. To overcome these limitations, advanced topologies like the fat tree architectures are used. The fat tree is inspired by the tree data structures, but unlike conventional trees, it increases the bandwidth near the root and introduces the redundant paths. This design ensures that even if some components fail, the network continues to function with minimal performance degradation. Now I would like to explain the second topic, fat tree topology, with a detailed explanation. The fat tree is a multi-rooted hierarchical network topology specially designed for high performance computing and data center environments. It provides multiple equal cost paths between nodes, ensuring efficient traffic distribution and tolerance. Topology is divided into three main structures: edge layer, aggregation layer, core layer. The edge layer is also known as access layers. It directly connects to the servers and it is responsible for initial packet forwarding. The aggregation layer connects multiple edge switches and acts as an intermediate routing layer, providing multiple paths to the core layer. The core layer is the most top layer that serves as backbone of the network, offering high bandwidth connectivity and full interconnection with aggregation switches. Key design properties and K-ARI fat tree. The one of the key point of the K-array fat tree is that the near the root factor, they have higher band compared to the lower links. This creates an bottlenecks and ensures efficient handling of large volumes of traffic. A fat tree is often defined using a parameter K, which represents the number of ports per switch. In a K-array fat tree, the number of ports is equal to K. Each port contains K by 2 edges and switches K by 2 aggregation switches. The total number of serves that can be supported is given by K cube by 4. This structured design ensures uniform traffic distribution and provides a high level of redundancy within the network. Types of failures in data center network. Fault resiliency in fat tree networks must address various types of failures, like link failures are the most common and occur due to cable damage or disconnection. Switch failures may arise due to hardware malfunctions or software crashes. Nodes or several failures typically let application level operators may fail you completely disrupt network connectivity. Power failures may cause rackets and pods go to offline, significantly impacting systems performance. Additionally, congestion induced failures occur when excessive traffic leads to the packet drops, which may behave similarly to the logical failures. Now I would like to see the core concept, fault resiliency. Fault resiliency refers to the ability of a system to detect failures, isolate faulty components, recover quickly, and maintain continuous service. In a factory networks, this is achieved through a combination of redundancy and intelligent routing mechanisms. The presence of multiple alternative paths ensures that the network can continue functioning even when certain components fail. Fault resiliency mechanisms. The primary mechanism that enables fault tolerance in factories in path redundancy, where multiple equal path exists between any two servers. If one fails, traffic can be immediately rerouted through another available path, eliminating single points of failure. Equal cost multipath routing, ECMP, further enhances this capability by distributing traffic across multiple paths with equal cost using hashing techniques, thereby improving load balancing and reducing congestion. Fast failure detection techniques such as heartbeat signals, linked layer detection, bidirectional forwarding detection (BFD) allow the system to identify faults within milliseconds. Once a failure is detected, fast rerouting, that is FRR mechanisms, redirect traffic without the need to recompute the entire route networking. Loading balancing techniques include hash-based, flow-based, and adaptive routing, help preventing hotspots and ensure efficient utilization of resources. Additionally, over provisioning of bandwidth ensures that the network maintains performance even during failure conditions. Data structures supporting fault resiliency. Efficient data structures play a crucial role in implementing fault resilient fat tree networks. The network is typically represented as a graph where nodes correspond to the switches or server and the edges represent communication links. Adjacency lists are used for memory efficient storage of large scale networks. Rerouting routing tables often improving used hashing allow constant time looking up for forwarding decisions. Priority queues are used in short path algorithms such as Dijkstra's algorithm to efficiently select optimal routes. Tree based indexing techniques are also employed to support hierarchical routing and scalable data access. Next topic is fault tolerant routing algorithms. Fault tolerant routing algorithms is nothing but several algorithms are used to ensure fault tolerant routing in fat tree networks. Dijkstra's algorithm, it is also used to compute the shortest path and it can also recompute routes dynamically after failures with a time complexity of fig of v log v. Breadth first search BFS goes in this pattern. I'm just showing a picture of how it does go. And now I start explaining about BFS. BFS follows which principle? It follows the stack principle. BFS is used in unweighted networks to quickly alternative path, multi-paths routing mechanisms, multiple active paths simultaneously, enabling instant switching during failures. Failure-aware routing algorithms proactively avoid routing and update algorithms proactively avoid faulty nodes and update routing algorithms dynamically. Software defined networking SDN introduces a centralized control mechanism that dynamically updates routing decisions, improving fault handling efficiency. Performance metrics for fault resiliency. The effectiveness of fault resiliency in fat tree networks is evaluated using several performance metrics. Through output measures the amount of data successfully transmitted through the network. Latency indicates the delay experienced in communication. Next, packet loss rate represents the number of packet lost due to failures or congestion. Recovery time measures how quickly the network can restore normal operation after failing. Advantages of fault tree fault resiliency. Fat tree topology offers several advantages including elimination of a single point of failure, high bandwidth availability, excellent scalability, efficient load balancing and fast recovery from failures. These features make it highly suitable for modern data center environments. Limitations and challenges. Despite its advantages, the fat tree topology also has certain limitations. It involves complex routing mechanisms, increased hardware costs and significant cabling complexity. Additionally, it requires advancing algorithms and intelligent control mechanisms to manage network operations effectively. Now let us talk about real world applications. The fat tree networks are widely used in cloud data centers, artificial intelligence and machine learning clusters, big data processing systems, supercomputers and enterprise networks. Major technology use companies are Google, Amazon and Microsoft. They utilize similar architectures to achieve scalability and reliability in their infrastructure. Comparison with traditional T. In comparison to traditional T topologies, fat trees provide multiple paths instead of a single path, resulting in higher fault tolerance. They offer significantly higher bandwidth and better scalability, whereas traditional trees suffer from limited bandwidth and poor scalability. Example scenario: consider a scenario where the link between aggregation layer and the core layer fails. In traditional topology, this would result in disconnection of an entire branch, but in fat trees, it is automatically rerouted to alternate core switch, that is ensuring to no service interruption. Conclusion, the factory topology, it is a powerful and scalable network that designs high faulty resilience through the use of redundant paths and intelligent routing mechanisms, efficient data structures, and it plays a crucial role in modern data centers, enabling highly reliable, high performance communication and supporting the growth demands of distributed computing systems. And with this, I would like to conclude my topic, and I thank my faculty for giving me this wonderful opportunity. And thank you everyone for giving me this gold honor opportunity to express a tech talk. Thank you.